Hello everybody. Let's start the chapter probability distribution. So far, we have studied probability in terms of set theory. Set theory is actually an abstract concept, and we have studied some concepts like union. We generally represent this union as a plus symbol, and the intersection of two events, that is generally represented by multiplication or dot symbol. So a sense of addition multiplication has been introduced in this way, but we can hardly do many mathematics with this kind of concepts or with this kind of sets. Hmm? If we need to further improve this theory and develop this theory, we require a fundamental result, and we always have a tendency to represent all the or any new theory with our old relatively developed results. And luckily we have the theory of real and complex numbers. Along with that real and complex numbers, a lot of development has been done with algebra and analysis of real and complex numbers. But over here, we shall mainly discuss about the real numbers. So hopefully this chapter would become a bit easier relative to the previous chapter. And after introduction of this kind of new concept that is called the random variables, hopefully this chapter would be much more easy to you. Okay. What is a random variable? Random variable is actually, you can define the random variable as a function which relates the event points in the event space to the points of real numbers. Each and every event point in an event space related to certain random experiment is now associated with real numbers. Okay, so this is the concept of random variables, and this kind of association or this kind of correspondence would facilitate us to study the event points through real number set of real numbers. Okay, hopefully as we know the mathematics on real numbers, and in that case hopefully the concept or the technique would be much more easier. That was the main idea in order to establish or in order to define a random variable. So what is a random variable? Random variable is it's actually a function. Generally, if capital S, suppose capital S is the event space related to certain random experiment E, and suppose U is an event point belonging to that event space capital S. Okay, and a random variable X is a function from S to the set of real numbers R. Okay, a real random variable. It is a function from the set S to the set of real numbers R, such that each and every event point in this in the event space capital S would have an associated real number that we call it x of u to the event u. Okay, and in this way we define the random variable, and sometimes it is also called variate. So that is the definition of random variable, and sometimes it is also called stochastic variable as well. So we shall mainly refer to the word random variable. So that is the definition of random variable. Now let us try to understand how to implement this random variable. And along with this definition of random variable, we need the definition of spectrum. What is a spectrum? Suppose we have a random variable, and what is the function of random variable? The function of random variable is to associate or is to establish a correspondence with the elements of the set capital S, with these elements of the set capital S and the elements of the set of real numbers. That is the main function of random variable. Now, if random if this is a function, so x is a function, although it is called a random variable, but it is basically a function. And the range set of this function, is called the spectrum of the random variable. And if this spectrum is a continuous set, then we call it a continuous random variable. And if it is a discrete set of real numbers, then we call it a discrete random variable. So in this way, we define discrete and continuous random variables. So roughly, we have defined mainly four definitions. The one is the definition of random variable. Second one is the definition of spectrum. Third one is discrete random variable, and fourth one is continuous random variable. Okay. Now let's try to understand the idea of random variable by some examples. And over here, before going to the example, we shall stick to certain notations, because without these notations, it would not be possible to understand all these examples. Okay. Over here, we generally say that if capital A is a set of real numbers R, and U is a point, an event point from the event space, then X belonging to capital A, X of U belonging to capital A, what does it mean? It means that this X belonging to capital A means that X belonging to capital A means that it should be the collection of all values of the random variable X at the point U, such that U belongs to the set of real U belongs to the event space capital S. Okay, so this event U belongs to the event space capital S. This is equivalently written in this way, that X belonging to capital A, with of course X of U belonging to the set capital A. In general, in place of writing X of U belonging to capital A, we generally write X belonging to the set capital A. And sometimes it happens that the random variable X has only a single value small a. Then it means that it refers to the set. We shall consider the all such elements of the set capital S with X of U is equal to the value small a. Okay. Sometimes we shall refer to this kind of inequalities or semi-open intervals. What does it mean? It means that this should be the collection of all values of the random variable X or X of U, such that U belongs to the set capital S and the value lie in between A and B. That means the value of the random variable lie in between A and B. So apparently it may look that a less than x less than is equal to b is actually an interval. But in the subsequent examples, we will prove that this is not always a continuous interval. It may be a discrete set of points as well. How? So let's go through these examples. Hopefully this concept would be much more clear if we consider this example. And I'm coming about these semi-open intervals later on after introducing all these intervals. So let's directly go to these examples. Suppose we consider the throwing of a die. Die means generally die is used in case of in the game of Ludo. So die should have six faces. One face would contain a single dot, another face would contain double dot, then three dots, then four dots, then five dots, and then six dots. So these are the possible outcomes of throwing a die. When a die is thrown, then these are the possible outcomes. Now, we are trying to define a random variable on this event space. Over here, this is this total collection of 6 points that should be our event space. In many books, they have written as 1, 2, 3, 4, 5, 6, but over here I'm not writing them by 1, 2, 3, 4, 5, 6. Rather, we actually get certain dots. That's why I'm writing these dots over here. Okay. Now we can associate few numbers with these dots, and that numbers may be 1, 2, 3, 4, 5, 6. That numbers may be 1, 2, 3, 4, 5, 6. So how would be the associated um, technique? That means how can we associate these outcomes with these random values, with these values? We can write it in this fashion, that suppose the random variable x associates this event single dot, this event single dot with this value 1. Okay, then it associates the event double dot with the value 2. It associates the event triple dot with the value 3, then 4 dots with the value 4, then 5 dots with the value 5, and 6 dots with the value 6. Got it? So that might be a certain kind of association or certain kind of correspondence that is actually established by this random variable capital X. So if we say x is equal to 3, if we say x is equal to 3, then x is equal to 3 would represent this outcome triple dot. Alright. So over here I have defined a random variable x, and we know that on a single set we can define many functions. More than one functions can be defined on a single set, and event space is a kind of set. Therefore, we can define more than one random variables on a single event space. We can define another random variable y in a random fashion. Okay, we are defining random variable in a random fashion or opposite fashion. We can define the random variable y in this way. It does not always mean that as we have only one dot, double dot, three dot, four dot, five dot, or six dots. So we'll have to always assign these values 1, 2, 3, 4, 5, 6 with all these outcomes. We may arbitrarily assign the values. Suppose over here I have assigned the value 11 with this first dot. Then the value 29 with this second dot, the value 43 with this third dot, then the value 5 with this fourth dot, 4 dots, the value 88 with this 5 dots, and the value 1026 with this 6 dots. So this association would be in our hand, and we shall use this association of this kind of real numbers as per our requirements. Okay, so that should be the definition of or the use of random variable. And over here these random variables can be written in different fashion. Over you see, suppose we consider the even phases. Even phase means the outcome would contain only double dot, 4 dots, or 6 dots. So we can write it in this way: x belongs to the set 2, 4, 6. Okay, and in terms of y, we should write this even phase in this way: 5, 29, 88. So in this way, we can define different events in terms of the set, in terms of capital X and capital Y. So over here, the spectrum of the variable X, what are the possible values? These are the possible values of the random variable X. Okay, 1, 2, 3, 4, 5, 6. Therefore, the spectrum of the random variables, that would be actually the range set of the function X, and that should contain these 6 numbers starting from 1 up to 6, all the integers in between 1 and 6. But over here, if you suppose consider the random variable y, in that case the spectrum should contain these 6 values: 11, 29, 43, then 5, then 8, then 1026. So I am writing these values in increasing order, and we can say that this y has this kind of spectrum. And you see, in terms of y, if we now try to write it in this way, suppose 0 less than y less than or is equal to 11. Apparently it look that yes, it is a continuous interval, semi open interval. It may look like that it is a semi open interval like 0 comma 11. Hmm, this kind of semi open interval. But if you look at this a bit carefully, the possible values of y in between 0 and 11, the possible values are 5 and 11. Got it? So what is 5? 5 represents the outcome 4 and 11 represents the outcome 1. So this event is actually the collection of this single dot comma 4 dots. Okay, so this event, although it looks like a continuous interval, but this event actually contains only two outcomes. So apparently, although these events look like a continuous interval, but it represents only two outcomes, and that is the beauty of random variable. That this kind of discrete outcomes, so this kind of discrete sets can be written in terms of a set of real numbers or a set like an interval. So over here now let's consider this idea, that is an important idea. We shall always use semi-open intervals. Why semi-open intervals are used over here? Why do we use this kind of semi-open intervals? Because suppose we consider, actually our target is to always apply the addition, the third axiom of probability. Then the third axiom means whenever we have two distinct or disjoint events like A and B, then these events A and B, if these two are disjoint, then we can write probability of A union B can be written as probability of A plus probability of B. So if we have two disjoint events, then we can write probability of A union B or A plus B is equal to probability of A plus probability of B. So over here we are trying to reproduce disjoint events. And if it is possible to represent these events in terms of intervals, that becomes a much more easier concept. So over here, if we try to reproduce them by open intervals, consecutive open intervals like A comma B and B comma C, then you see that these two intervals are of course disjoint intervals, but their union does not produce the open interval A comma C. The point B is not included in both of these two intervals, but B is included in this total open interval A comma C. So we cannot say that union of A comma B and union of along with B comma C, these two union of these two intervals produces this interval A comma C. The point B is not present in this both of these two subintervals. And over here, if you consider the closed intervals, in that case, the closed intervals A comma B and the closed interval B comma C, these two are consecutive closed intervals. And of course, their union is again a consecutive closed interval starting from A up to C. Starting from A to C, we will get a closed interval. But the problem is that over here B is a common point to both of these two closed intervals. So these two closed intervals are not disjoint intervals. In order to get some mutually exclusive, or in order to deal some mutually exclusive events, we need to get certain mutually exclusive intervals as well. Got it? These are the problems with this kind of open intervals and closed intervals, and in order to overcome this problem, we generally use this kind of non-conventional intervals like semi-open interval a comma b. It is open in left and closed in right side, and the next immediate open interval can be considered as semi-open interval can be considered as B comma C. And you see these two are disjoint intervals, and their union would be a similar interval like A comma C. That's why we generally use this kind of uncommon semi-open intervals. Got it? And the same effect can be generated if we consider the opposite kind of semi-open intervals like closed in left side and open on the right side. This kind of semi-open intervals can also be used, but we generally use the semi-open intervals which are open on left and closed on the right side. And this kind of semi-open intervals have a special benefit that we shall study in our subsequent part. So that's why we use this kind of unconventional semi-open intervals. Got it? Now let's try to understand the idea of a random variable through few more examples. Over here, suppose we consider a game of cards. Hmm? A game of cards is considered, and in generally we know that in a game of cards we have 52 cards, and 52 cards have are divided into four different suits, and each and every suits have the cards starting from ace, then 2 3 4 5 6 up to 10. And suppose jack, queen and king have the values 11, 12 and 13. Then what we are doing, jack, queen and king, these are actually some symbols. We are associating some numbers with them. Okay, so if we define a random variable such that start my ace has the value 1, then 2, the card having 2 digit 2 has the value 2, and then 3, then 4 and so on. Similarly up to 10, and then jack has the value 11, queen has the value 12, and 13 refers to the card king. So jack, queen, and king. So in this fashion, we can associate few numbers with the cards. And if we suppose refer to the value x is equal to 1, what is x is equal to 1? X is equal to 1 should represent the card S. And how many S's are there? You see, in four different suits, we shall have four S's. So although x is equal to 1 represents a single number, but it is associated with four different aces belonging to four different suits. So x is equal to 1 would represent four even points. All of them are aces of different suits. Got it? So if we want to find out the probability of the event, so x is equal to 1 would denote the event S. And what will be the probability of the event? X is equal to 1. You see, if you want to consider the classical definition, then by classical definition 4 S's are there out of 52 cards. So the probability would be is equal to 1 by 13. In this way, we compute the probability of an event represented in terms of random variable. So, so far it may look that then what is the benefit of using the random variable? We are writing x is equal to 1, and we could also write s, just simply in this term s in place of x is equal to 1, and we would get the same this kind of probability. So that would be evident from the subsequent discussion, but let me try to discuss a few more examples. For example, suppose we consider throwing of a coin. Hmm? Then in a coin we have two sides. One side is called head, and another side is called tail. So head can have the value x is equal to 0, and tail can have the value x is equal to 1. So if we get head in a particular coin, in a particular toss, we would say that we get the event x is equal to 0. If we get the event tail, we would say that we get the event x is equal to 1. So now the spectrum of x has only 2 points, 0 and 1, and their corresponding probabilities can be written in this way. Probability x is equal to 0 means probability of head, and probability x is equal to 1 means probability of tail. Got it? So in this way we can find out the probabilities, and this would be a bit little bit advanced, relatively advanced example. Over here you see we consider a Bernoulli sequence of events. And we know a Bernoulli sequence of events, each and every trial would have two events. One is success, another is failure. Okay. Now, if we define a random variable in a way that the random variable denotes the number of success in an event point. What are the event points? These are the possible event points. X is failure, 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 or success, failure, failure. We are considering three trials. So success, if success is denoted by small s and failure is denoted by small a, then we would have this kind of event points. These are the possible event points. Now writing them as failure, 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 or success, failure, failure, this may be a bit abstract and boring as well. So now if we define a random variable denoting the number of success, okay, the number of success in an event point, then you see it becomes a bit little bit easier for us to write. Suppose this FFF, this event can be written as the event x is equal to 0, because it does not have any success at all. So x refers to the number of success. This event does not have any success. So how many success are there? Zero number of success are there. That's why we are writing it as x is equal to 0. Now consider these three kind of events: success, failure, 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 success, failure, and then failure, failure, success. All these three events have a single success, and x is a random variable. We are going to define this random variable x as number of success. So each and every event we have only a single success. So we can say x is equal to 1 refers to this event, and so x is equal to 1 would collectively refer all these three events. So x is equal to 1 is an event containing these three event points: success, failure, 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 success, failure, and failure, failure, success. Got it? And now we can similarly define x is equal to 2 and x is equal to 3. And we can write that probability of x is equal to 0, that is what is the probability over here? Probability of x is equal to 0. You see x is equal to 0 refers to this failure, failure, and failure. Three failures over here. So the probability of failure, if we denote it by q, then q, the compound experiment, so it would be q square. In the now x is equal to 1. Over here x is equal to 1 has three events. Over here success, failure, failure. Probability of success is p, and probability of failure is equal to q. So it would probability of success, this s would give us the probability p, and these two events failure and failure, these two together would give us the probability q. Okay, so p, q, and q. So p, q square. How many such events are there over here? Three such events are there. So that's why 3 q square p would be the probability of the event x is equal to 1. Similarly, if you consider x is equal to 2, the probability would be 3 p square q. For the last case, x is equal to 3, we have 3 success, therefore the probability would be pq. So in this way, we define the random variable and we compute their probabilities. Alright. And over here, all these random variables are discrete random variables. You see, the random variables are taking the values sometimes 0, sometimes 1, sometimes 2, sometimes 5, sometimes 11, etc. All these random variables are discrete random variables. Now, let's consider one random variable that would be a continuous random variable. Suppose we have a rod. we have a rod of 10 centimeter long, although it is not a straight line, but suppose this is a rod, and it is a 10 centimeter long, and we are trying to define a random variable x denoting the length of an arbitrary point. Suppose this arbitrary point is p. Hmm. Length of arbitrary point, this much length. We are trying to define this much length. Hmm. We are trying to define this much length as equal to x. Then what would be x? So starting from 0 up to 10, so this random variable x would have any value in between 0 and 10. So we can say that random variable would be a continuous random variable because the spectrum of that random variable would be starting from 0 to 10. Okay, so that would be the spectrum of the random variable. So this is an example of the random variable, and that is actually a continuous random variable. Okay, so these are some examples of random variables. Different examples has been given for continuous random variable and different discrete random variables. Now we are going to define a function that is called the distribution function of related to this random variable x. Distribution function of a random variable x. What is this? It says that f should be a function from the set of real numbers r to the open to the closed interval 0 comma 1. How do we define this function? This should be f of x, that should be probability of minus infinity less than x less than or is equal to small x. F of x is equal to probability of minus infinity less than x less than is equal to small x. We know that probability can never be a negative quantity, so probability is always greater than is equal to 0, and probability of any event that is always less than is equal to 1. Therefore value of the function f, capital F, value of this function capital F will have the values in between 0 and 1. That's why the range set has been taken as 0 1, the codomain set. Okay, so f of x would represent the probability of certain event. What kind of event? This kind of event, minus infinity less than x less than or is equal to small x. Small x is a real number and capital X is a random variable. Okay. Now, what would be the properties of this kind of random variable f? I am going to study in this lecture today. I am going to study 5 properties of this function capital F. And in future we shall sometimes refer to the curve representing the function capital F, and that curve will always be referred to as the distribution curve of the random variable. Okay. And you see, we know that the value of the function f lies in between 0 and 1. Therefore, if we want to draw the distribution curve like this kind of distribution curve, maybe this kind of distribution curve, the maximum value would be is equal to plus 1. So that value would be the straight line y is equal to 1, and the minimum value is 0, so y is equal to 0. So we can say that the value of this function are bounded between two lines. This is the first line. One line is y is equal to 1, and the second line is this axis, x axis, that is actually the straight line y is equal to 0. That's why we say that the value of the function f is always bounded in between these two lines, y is equal to 0 and y is equal to 1. Okay. And this is a theorem that generally has been selected many times in your exam. Sometimes only one or two part has been selected to prove in exam. Sometimes the entire theorem has been selected. Anyway, so I am going to prove this result, this theorem, and that is defines a very important 5 properties of the function f. We can prove that this function, this distribution function f satisfies all these 5 properties, and conversely, it can also be proved that if a function f satisfies all these 5 properties, then that function f will be a distribution function of some random variable. Maybe we don't know what is the random variable, but that function f would be a distribution function of certain some random variable. Okay, so we can say that these five properties are actually necessary and sufficient condition of a function f to be a distribution function. So let's prove these properties one by one. I am proving all these properties by certain propositions over here. What are these properties? It says that the first property, that the distribution function f should be monotonic non-decreasing function. Okay, if f is a distribution function, then it should be a monotonic non-decreasing function. Monotone non-decreasing function. All right, we'll have to prove that the function f is a monotone non-decreasing function. That means monotone non-decreasing means a greater than b. It should refer to the fact that f of a, hmm, f of a is f of a should be greater than or is equal to f of b. It may have strict inequality, it may not follow the strict inequality, equality may occur. So this is the idea of monotone non-decreasing function or monotone increasing function. Okay, so we are going to prove this result, that the function capital F is a monotone non-decreasing function. How to prove this result? We have this definition: f is equal to probability of minus infinity less than x less than or is equal to small x, where x is a real number, of course. We suppose that b greater than a and b are two numbers, and where b is greater than a. Now you see, if we draw a straight line, say maybe this is a straight line, and this left end may represent the number minus infinity, and suppose this is the value b, and this is the value a. These are real numbers. Okay, a and b is greater than a, b is greater than a. Then starting from minus infinity to b, this interval minus infinity to minus infinity less than x less than is equal to b. This interval can be written in this way: minus infinity to the interval to the point small a, semi open interval minus infinity to a, and then another semi open interval starting from a to this set b. Okay, so we can write that this total interval is the union of this first interval, that is actually an infinitely large interval starting from minus infinity to a, and another semi-open interval a less than capital X less than or is equal to b. And you see over here these two intervals, this interval and this interval, these two intervals are mutually exclusive or disjoint intervals, and so we can now apply the third axiom of probability. We can say the probability of this right hand side, probability of minus infinity less than x less than or is equal to b, that is equal to probability of minus infinity less than x less than is equal to a plus probability of a less than x less than or is equal to b. And from the definition of this function f, you see, if you consider this left side, this left hand side would represent the value of this function capital F. This left hand side would represent the value of the function capital F at the point B. At the point B. Okay. And this portion would be the value of the function f at the point small a. That directly follows from this equation number 1, the definition of the function capital F. Therefore, this left hand side can be written as f of b is equal to the first term is equal, that is actually the f of a plus probability of a less than x less than is equal to b, or in other words, as because f of a and f of b are two finite numbers, therefore you can say that probability of A less than X less than or is equal to B is equal to AB minus f of A. Got it? AB minus f of A, and over here please try to remember this formula by heart, because this formula should be used in future whenever required. This is a standard formula, and this formula itself has been selected in exam many times, that probability A less than X less than is equal to B, that is equal to AB minus f of A. Okay. And as you see, this expression, this right hand side expression is greater than or is equal to 0. So we can say from this expression, from this result, that AB, this first term, is greater than is equal to second term. So AB is greater than is equal to f of A for B greater than A. Alright. So this is the proof of this result. So this is the first property. Next, we are going to prove this second property, f of minus infinity is equal to 0. F of minus infinity is equal to 0. What does it mean? It means f of minus infinity means that limit extending to minus infinity, a printing mistake is there. Okay. Limit extending to minus infinity f of x should be is equal to f of minus infinity. So we are going to prove this result, limit extending to minus infinity f of x, that is equal to f of minus infinity. And in order to prove this result, we are taking an interval an. An is this kind of interval, minus infinity less than x less than is equal to minus n, where n is a positive integer or a natural number. Then what is the limit that n tending to infinity an? In general, when we take the limit n tending to infinity, we will get minus infinity over here. So we will have this kind of result, minus infinity less than x less than or is equal to infinity. But you see, as per the definition of random variable x is a function which associates the events with the set of real numbers. Okay, set of real numbers. So the values of x, the values of this random variable x is always a real number. So if x is a real number, then x is always finite. The value of x should always be finite. But over here, minus infinity less than x less than is equal to minus infinity. What does it mean? It means that x is equal to minus infinity. Okay, so this is not a finite number. Minus infinity and plus infinity, these are not finite number. These are called extended real number, not any real number. So real number, remember, real number should always be a finite number. So over here, the value of x is equal to minus infinity. It means that x is not taking any real number at all, and that would be possible only when we have the impossible event. This is not actually possible any times at all, because x is always a real number. So x cannot take the value minus infinity. So that is possible only for impossible event. Okay. So over here, this limit n tending to infinity an, this limit actually refers to the impossible event. And as because it is an impossible event, we can say that probability of this impossible event is equal to 0. So we have the result that probability of this impossible event an, the probability of limit ending to tending to infinity an, that becomes is equal to 0. Now you consider these intervals an. What are these intervals? An is equal to minus infinity to plus infinity. So consider a line over here. Suppose minus infinity is situated over here. This is our minus infinity, and maybe this is our the point 0. This is the point 0. Say this is minus 1. Then this may be minus 2, and so on. In this way, suppose this is our minus n, and then we shall have minus n plus 1 within bracket. Sorry, plus 1. So the interval starting from minus infinity to starting from minus infinity, hmm, starting from the minus infinity, the open bracket, and up to minus n plus 1. Okay, this kind of interval. Minus infinity, minus x, minus of n plus 1, that means minus n minus 1. This would be a subset of the interval minus infinity to minus n. Got it? So this would be a subset of the interval minus infinity to minus n. That is the interval an. And what is the left hand interval? Left hand interval is an plus 1. So we can say that an plus 1 is a smaller set relative to an. What is the observation? Observation is that as we increase the index n, the set an would become smaller and smaller. So a1 relative to a1, a2 would be smaller, relative to a2, a3 would be smaller. That means this a1, a2, a3, these events become smaller and smaller. So we can now say that this sequence of events are contracting sequence of events are smaller, getting smaller and smaller sequence of events, and ultimately, what is the limit of all these events? The limit of all these events becomes an impossible event that does not contain any possible event point at all. Hmm? So it is decreasing and this is tending to 0. And we know that for this kind of events, we can interchange the probability and the limit. So we will have limit n tending to infinity probability of an, that is equal to probability of limit an. And we have already proved that probability of limit an is equal to 0. Hmm? And so we can say that limit of this left hand side means minus infinity less than x less than or is equal to minus n. For integers n, of course, then this value becomes is equal to 1, and this probability is actually this probability of minus infinity less than x less than is equal to minus n, that is actually f of minus n. Okay, so we have proved the required result with the limit that n tending to infinity, but we have to prove the same result with the limit x tending to minus infinity. Over here n is an integer and over here x is a real number. Got it? So from integer to real number we have to make a jump. And how to make such jump? That we know that for each x we have a real number n such that minus n minus 1 less than x less than or is equal to n. For each real number x, negative real number, you will get this kind of interval. Suppose x is equal to 2.5. Then this over here we will have minus 2 and on the left we will have minus 3. So for all such real number x, we'll have two numbers. One is minus n and second one is minus n minus 1, satisfying these two inequalities. And what is the benefit of this kind of inequality? The benefit is that if we take the limit n tending to infinity, then of course x tends to minus infinity. And if further we take the limit x tending to minus infinity, then of course this smaller number would move towards minus infinity, and then it means that n would tend to infinity. So n tending to infinity and x tending to minus infinity are equivalent results. Okay, and therefore we can write that this left hand side limit of this kind of expression, as we have already proved that the function f is a monotone non-decreasing function, so f of minus n should be less than is equal to f of x, and that should be less than is equal to f of minus n. So f of minus n minus 1 less than is equal to f of x less than is equal to f of minus n. And so we take the limit where n tending to infinity and x tending to minus infinity, both are equivalent results. So we can now finally say over here this left hand side is equal to 0, the right hand side is equal to 0 because of this relation number 2. Okay, and as because both of these two left hand side and right hand side are these two limits are equal to 0, so we can say that the limit of this middlemost term, this limit exists, and the value of this limit is equal to 0. So in this way, we have proved the second property, that f of minus infinity is equal to 0. We proceed the immediate next result, that f of infinity is equal to 1. F of infinity is equal to 1. In order to prove this result, we have taken a different kind of event, an. In the previous result, we took minus infinity less than x less than is equal to minus n, negative integer. Okay, and now we are taking in this kind of event, that minus infinity less than x less than plus n, or the positive integer. Why? Because we need to, there is a one more printing mistake. X should tend to infinity. Anyway, so f of infinity means x tending to infinity. F of x, that should be is equal to f of infinity, and that should be is equal to 1. Our target is to show, or our target is to take the limit x tending to plus infinity. That's why we are taking these positive integers. Okay. So if we take the limit n tending to infinity, we will have minus infinity less than x and less than is equal to plus infinity, and that is actually the total event space capital S, and we know that probability of that event space is equal to 1. So probability of in this event n tending to infinity an, that probability should be is equal to 1. Hmm. And now you see, in the similar technique that I demonstrated over here, you see over here, I started with minus infinity up to, suppose this may be the integer n, and this may be, this position may be the integer n plus 1. So this much portion would be our a n plus 1. This much portion would be is equal to an plus 1, and this much portion is equal to our event an. Got it? So we can say that an is a subset of an plus 1. That means as we increase the index, the subset is getting bigger and bigger. So these sets are increasing sequence of events, or expanding sequence of events. Got it? And we know for contracting or expanding sequence of events, this result, limit n tending to infinity, limit and probability can be interchanged. Limit n tending to infinity, probability of n is equal to probability of limit n, that is equal to 1. So now limit n tending to infinity, probability of minus infinity an means minus infinity less than x less than or is equal to n. So this probability should be is equal to, one more printing mistake is there, it should be is equal to 1. Got it? It should be is equal to 1. This one should be, this 0 should be is equal to 1, and this 0 should also be is equal to 1. So in any case, we can say that limit n tending to infinity, f of n becomes is equal to 1. And by the similar technique, we can say for any real number x greater than 0, we have n less than x less than is equal to n plus 1. And so by the same technique, as because n is a monoton non-decreasing function, f of n should be less than or is equal to f of x, and that should be less than is equal to f of n plus 1. So this limit is equal to 1 by relation number 2, and this limit is also is equal to 1 by relation number 2. So we can say that limit in this middlemost expression, that means f of x, limit of f of x as extending to infinity exists, and this limit is equal to 1. Got it? So in this way, we proved that f of infinity is equal to 1. So the proof was very similar to the previous result. Now we are going to prove another result, that the function, the distribution function of any random variable x is a continuous function on the right side. It is a continuous function on the right side. It is a right continuous function. So what is right continuity? Right continuity means the right limit f of x plus 0, right limit f of x plus 0, that should be is equal to value of the function f at the point x. If we can prove this result, then we would be able to conclude that the function f is right continuous at the point x. Okay. So we are going to prove this result, and in order to prove this result, we are taking this kind of intervals: a less than x less than or is equal to a plus 1 by n. Hmm? A less than x less than is equal to a plus 1 by n. So you see this this may be the position of the point A, and if n is equal to 2, then this is a plus half. Suppose n is equal to 2, then a plus half may be this kind of a point, a plus half. Then a plus 1 by 3 would be more closer to the point a plus 1 by 3. This kind of point would be more close to a. Then a plus 1 by 4 would be relatively more close, a plus 1 by 4. So what we are observing over here, we are observing that this is our a4, hmm? This is our a3, this much is our A3. Got it? So A3 is a superset, A4 is a subset. This set is smaller set. As the value of n increases, the sets are getting contracted. So we can say that AN is a contracting sequence of events. AN is a contracting sequence of events, and along with that, we can say over here you see this is the definition of A. As n tending to infinity, as n tending to infinity, we are taking the limit as n tending to infinity. If we take the limit n tending to infinity, we have a less than x from this first inequality, and from this second inequality, what we have, x is less than or is equal to 1, because n tending to infinity, therefore this expression should value is equal to small a only. And that is, you see, these are contradictory results. Why contradictory? Because if x is greater than a, then x cannot be less than or is equal to a. I'm saying again that if x is greater than a, then x cannot be less than or is equal to a. So we have some contradictory results. And this contradictory result means that x does not have any real value at all. So this contradictory result is satisfied only when only when this event is an impossible event. This is never possible at all. So never possible means it should be an impossible event. That's why I have written that this kind of event means it is an impossible event, that is denoted by the symbol null set. Okay. So this is an impossible event, and the probability of such impossible event is equal to 0. Hmm? And I have concluded that this AN is a contracting sequence of events that I have shown over here, that AN is a contracting sequence of events. And as because this is a contracting sequence of events, therefore we can interchange probability and limit. We can say that n tending to infinity probability of an, that is equal to probability of limit n tending to infinity an, and that is ultimately is equal to 0. I have proved that probability of limit n tending to infinity is equal to this event. The probability of this event is equal to 0. And then what is this? What is an? An is equal to the event a less than x less than is equal to a plus 1 by n. So this is in the form that that is probability of a less than x less than is equal to b. I have proved this result earlier over here in the first proof, that in this first proof over here in this equation number 1, you see, if probability of a less than x less than or is equal to b, it means that ab minus f of a. I am going to apply this formula. So over here we shall get the result, this result. Probability of a less than x less than is equal to b. Consider this a plus 1 by n as equal to b. This is the expression. You can consider this expression as equal to b. So what we have, f of b minus f of a. Alright, probability of this expression is equal to f of a plus 1 by n minus f of a. So this expression becomes is equal to limit n tending to infinity f of 1 by n minus, this should be treated as a constant quantity because this second term does not involve anything related to the index n. So we can take n tending to infinity, limit probability of a tending to infinity, this value would be same as this f of a. Got it? So now after taking the limit, what we get, this should be a plus 1 by n with n tending to infinity, means it should be right limit f of a plus 0. And from this result we can say that f of a plus 0 is equal to f of a, and this proves that the function f is right continuous at the point small a. In fact, at any point the function f is right continuous. Okay. And now the last part of this result. Last part says that if probability that x is equal to a, if probability that x is equal to a is a positive quantity, then the function f has a jump discontinuity. Then the function f has a jump discontinuity on the left at x is equal to a. And what would be the height of the jump? The height of the jump should be is equal to the probability that x is equal to a. This is the final result that I am going to prove over here. And in order to prove this result, I am considering opposite category of interval, a minus 1 by n less than x less than is equal to small a. What does it mean? You see over here we are drawing one figure. This may be a figure. A minus 1 by n less than x less than is equal to a. So this is suppose a. This is suppose our a. And this is suppose for n is equal to 2, we get a minus 1 by 2. Okay, then a minus 1 by 3 would be a little larger value. A minus 1 by 3 is kind of little larger value. So a minus 1 by 3, this value, this interval starting from this interval, this is a3, the interval a3. And this kind of interval starting from this a minus 1 by 2 up to this point a, this interval would be our a2. So what we observe is that a2 is a larger set, a3 is a smaller set. So a2 is a larger set and a3 is a smaller set. It means that as we increase the index, the sets are getting smaller and smaller. So a4 would be relatively more smaller set. Okay. So a1, a2, a3, this is actually a decreasing sequence or contracting sequence of events. And if we take the limit as n tending to infinity, then this left hand side would be is equal to small a. So we can say that a less than or is equal to x, and x is less than or is equal to a. You may observe that we know that after taking limit, this kind of strong inequality becomes loose inequality. So equality may arise after taking limit. That's why in place of minus, in place of this strict inequality, I am writing a less than or is equal to x. Okay. So a less than or is equal to x and x less than is equal to a means that x should be is equal to the is equal to the value small a. And therefore we can say that this limit n tending to infinity an should be same as limit x tending to a. So probability of limit n tending to infinity an, that should be is equal to probability of x is equal to a. And as I told you earlier that this an is a contracting sequence of events. Therefore we can say that again, as because it is a contracting sequence of events, so we can now interchange this limit and probability. And the probability of this second limit, probability of this n tending to infinity an, that should be is equal to probability of a. Okay. And therefore we can say that this limit of probability of an, what is an? An is equal to minus 1 by n less than x less than or is equal to a. So this is again in the form of f of a minus f of b form. Probability of f of a less than x less than is equal to a. So this can be written as f of upper limit minus f of lower limit, and that is equal to the probability that x is equal to a. Got it? And therefore we can say that this expression n tending to infinity is that is actually for f of 1 by n. So ultimately this expression is, what is this? This expression is nothing but the left limit f of a minus 0. Got it? This expression would be the left limit f of a minus 0. So you see that if this probability becomes is equal to 0, if this probability becomes is equal to 0, then only this left limit becomes is equal to the value of the function at the point a. So in that case only we can say that the function f is continuous on the left. But if it is not equal to 0, if it is greater than 0, then we should say that f of a plus a minus 0, this left limit, is not equal to f of a, and in such cases we can say that the function f has a jump discontinuity. And what is the height of this jump? Height of this jump is equal to this expression, probability x is equal to a. Got it? So this is the result. It says that the function f has a jump discontinuity at the point x is equal to a. The height of the jump being x is equal to the probability of x is equal to a. This is the height of the jump. Got it? So that's all for today. I wanted to discuss. Thank you.